Hello, this is Mrs. Taylor, and I'm going to show you how to simplify radicals with higher roots. So higher roots means roots more than 2. And so when you have roots that are higher than 2, sometimes your perfect roots can be your higher roots can be harder to spot. So we're pretty familiar with the perfect squares, but we might not be as familiar with the perfect cubes. And so our strategy for simplifying here is going to be to factor all the way down to the prime numbers and then spot groups of how many ever your root is. So in this case, we have a root of 3, so I'm looking for groups of 3. And so I'm just going to factor 75 first, and just a heads up, I'm using the mouse to write with, so my handwriting might be pretty bad. So 75 times 10 will give me 750, and then 75 can factor with 25 and 3, and then 25 factors to 5 and 5. So 5, 5, and 3, those are prime, so I'm done there. And then 10 factors into 5 and 2. So what I'm going to do is I'm going to circle my groups of 3. So I have a group of 3 5s. And then I have this 3 and this 2 left over. Remember, we're looking for prime numbers. And so what that means is that 5 times 5 times 5, that would be a perfect cube, because cube root is what number times itself 3 times will give you this number. And so if I took the cube root of 5 times 5 times 5, it would just be 5. So what we've been calling that is pulling out a 5 to represent that group of 5. And then whatever prime numbers you have left, go back inside the radical and multiply back out. So I'd have the cube root of 3 times 2, and then 3 times 2 is 6. So to have a simplified answer, I would need to multiply that back out. So really, really sloppily, this is 5 times the cube root of 6, and that would be my simplified form of the cube root of 750. If I put the cube root of 750 in my calculator and I put 5 times the cube root of 6 in my calculator, I'd get the same number when I pressed enter. So these are equivalent, it's just this is the simplified form. Alright, so let's move into territory where we have variables. So we do the same thing with the number that we did before. Factors of 48, let's say 12 and 4, and then I can factor the 12 using 6 and 2, and then 6 factors into 3 and 2, so now I have the prime factors of 6, and then if I factor 4, I'll get those prime factors as well. And again, it's a cube root, so I'm looking for groups of 3. And so I have 3 2's right here. And then I have this 3 and 2 left over. So I had this negative 2 outside. That doesn't change. I still have that negative 2. And then I have this group of 3 2's. So I pull out a 2 to represent that. Remember, the cube root of the 3 2's would be 2. And then inside the cube root, I'd be left with the 3 and 2. Okay, so I'm going to leave some space here because I know I have this variable coming up. And then I'm just going to write the cube root of 3 times 2. Now this example also brings up this negative. And remember, in class I told you that if you had a negative inside of an odd root, you need to pull the negative out as well. So I could pull that out as a negative 1 and just slap it over here so that it's multiplied by the numbers I've already got out front. Okay, so now let's look at the variable. It's v to the 7th, and really what that means is you have 7 v's underneath the radical. So you have 2 groups of 3 v's that you can pull out a v to represent. And I don't really want to write out 7 v's and circle them, so the shortcut that we learned is that you can take your root and divide it into the exponent. So 3 will go into 7, and you figure out how many times the root will go into the exponent, and that tells you what goes on the outside. So 3 will go into 7 twice, so that means that I have v to the 2nd power outside of my radical. However, there's 1 left over, a remainder of 1. So that means v to the 1st will go back inside the radical. And so, to simplify what all I have written out, I'm going to multiply the numbers. And then instead of writing v to the first, because you don't ever see that, I'm just going to write v, because the one's understood to be there. And so negative 2 times 2 would be negative 4. Negative 4 times negative 1 would be positive 4. So I have 4v squared, and then the cube root of, and then 3 times 2 is 6, and then I have that v. And so this would be the simplified form of your original expression. And so you would do the same thing with how many ever variables you had. So if you had a problem like this, you'd factor the 135 just like before, and then you divide 3 into 5 and 3 into 3 separately and work on those. So simplified, or simplifying, my process would look like this. 135 divided by 5, let's see, that'd be 117, I think. No, I don't think that's right. I better use my calculator. Hold on just a minute. 27, not 17. All right, and then if I factor 27, that would be 9 and 3, very sloppily. And then 9 would factor into 3 and 3. And so I have a group of 3 3s, and the reason why I'm looking for a group of 3 is, again, it's the cube root. Won't always be the cube root, but for these examples it was. And so I have that 3 out front to represent that group of 3. But I still had this 5, so I'm going to have to put that back into the cube root. I had a negative, and it's an odd root, so I need to bring that negative outside. And then 3 will go into 5 once, so I have 1x out here. And then there's a remainder of 2, so x squared. And then 3 will go into 3 once, so I have y out here. And then there's no remainder, so there's no y inside my cube root. And so now, after I write all that out, I have nothing left to multiply out. So I have my final answer. The cube root of negative 135 x to the fifth y cubed equals negative 3xy times the cube root of 5x squared. And that's how you would simplify with higher order roots.